So the time has now come for us to start addressing what many people think is the real stoichiometry problems, where we go from a certain amount of one substance to a certain amount of another substance. I use the roadmap approach, which is that everything is based around moles. So we can say I've got moles of a substance. I can convert moles of that substance to grams using grams is moles times molar mass. I can convert moles of one substance A to moles of another substance B by using the coefficients from the chemical equation. And then, of course, once I've got moles of B, I can convert to grams of B using the same grams as moles times molar mass, except here, of course, now using molar mass of B, whereas over here you would have used the molar mass of A. I refer to the A side and I refer to the B side. And so a lot of times, if you're given grams of one substance, you convert that to moles in step 1, convert moles of A to moles of B in step 2, and then moles of B to grams of B in step 3. So be referring to this roadmap during these next few problems. Sometimes I will explicitly show the roadmap. Other times I'll talk about the relationships that we see in there. So starting off, iron can be extracted from FeO according to the equation below. Make sure it's balanced before we do anything else. 1 iron, 1 carbon, 2 oxygens. Calculate the mass in grams of iron that could be extracted from 20 kilograms of iron 2 oxide. Okay, so assigning everything here, what do we know? We know things about the iron oxide, so I'm going to call that substance A, and we're asked about things for iron, so I'm going to call that substance B. So let's put all of that stuff in there. A is FeO, molar mass of FeO that we may or may not use. We obviously will. 71.85 grams per mole, and we got 20 kilograms or 20,000 grams of FeO. And then substance B, iron, we know the molar mass of iron, and the whole point is we want to get the number of grams of iron. So step 1 is where we go from the grams of FeO to the moles of FeO, throw everything into the grams is moles times molar mass relationship, 20,000 grams, moles times 71.85. Moles is 278.36 moles, and so that's what's now in this box. Step number 2, we convert moles of A, of FeO, to moles of iron, and we do that using the coefficients from the equation. Well, fortuitously, the coefficients are both 1. So moles of B, which is moles of iron, equals the 278.36 moles of substance A that we previously calculated. 1/1, so the moles of B, that's the moles of iron, 278.36 moles. That's what goes in this box. And finally, step 3, convert that to grams. 278.36 moles times 55.85 grams per mole. Thus, the number of grams of iron, 15,500. Other ways you could have done that, you could have just done it with a percentages, just multiplied the 20 kilograms by the 55.85 divided by 71.85 if you like ratios, but I would prefer to just think about one general relationship, one general process for solving stoichiometry, otherwise known as the roadmap. So iron obtained from blast furnace contains some sulfurs and impurity. This is removed during basic oxygen steel making by adding magnesium, which removes the sulfur as magnesium sulfide. 350 tons of impure iron used for BOS contain 0.02% of sulfur. Calculate the mass in kilograms of magnesium needed to remove all the sulfur. Well, the first thing is we know about sulfur and we're asked about magnesium. So therefore, we assign things. There's the sulfur, is what we know about. Molar mass, there's the magnesium that we are asked about for the mass. Okay. Now, of course, trouble is, we don't actually know what to put in here for the sulfur. We know that 350 tons of the impure iron contain 0.02% of sulfur. So the first thing we can do is calculate the mass of sulfur, which is 350 tons times the 0.02%, which equals 0.07 tons or 70 kilograms. So there we are, 70,000 grams can pop in there. Okay, so added a little bit at the start. Do you understand what we mean by percent? So let's go ahead and do it. Step 1, we have 70,000 grams of sulfur, molar mass 32.06. So therefore we have 2,183 moles of sulfur. Now for step 2, we need the coefficients of an equation. We don't have an equation. Well, we do, we just haven't written it out yet because we know we got sulfur plus magnesium making MgS. So we'll put that down here just so we got it. Magnesium plus the sulfur is MgS. So therefore the coefficients are both 1 and 1. That's jolly nice. So moles of B, which is of course magnesium, over the 2,183 moles of A, that's the sulfur, 1 to 1. So moles of magnesium, 2,183. That's what goes in that box there. Last step, convert the moles of magnesium to grams of magnesium. Multiply the moles by 24.3 grams per mole molar mass, which is 53,060 grams, or of course 53 kilograms. Even 53.1 kilograms. Reaction with CaCl2, Gareth, good old Gareth, obtained 2.49 grams of pure dry calcium oxalate from 4.69 grams of a mixture that contained potassium oxalate and other substances. Calculate the percentage of potassium oxalate in the original mixture. Well, here we've got a reaction in which we are told about the calcium oxalate and we're asked about the potassium oxalate. So let's put in colors there, pink for what we know, brownish for what we don't know. Set up the roadmap. Replace in the things, calcium oxalate, 2.49 grams, told the molar mass of that. Potassium oxalate, for which we are not told the molar mass here, but relatively straightforward to get it, is the unknown. So I'm not going to dwell upon things, just go through quickly enough or slowly enough to make sure we got the right numbers in. Step number 1, grams of calcium oxalate to moles. So 2.49 divided by 128 grams per mole, 0.0195 moles. Step number 2, going from moles of the calcium oxalate, which is 0.0195, over to the moles of potassium oxalate here. So we need the equation, coefficients of the equation, and what we find is that it's a 1-to-1 reaction. A-level examiners love 1-to-1 reactions for this stuff, don't they? So therefore, the moles of B, which is the potassium oxalate, over the 0.0195 moles of A that we just calculated as 1-to-1. So we've got 0.0195 moles here of the potassium oxalate, which we then convert to grams. 0.0195 moles times the 166 grams per mole. So in this sample, we had 3.24 grams of the potassium oxalate. Haven't quite finished yet. Just calculated that we got 3.24 grams of potassium oxalate, but we wanted the percentage of that in the original mixture. In the original mixture, we had 4.69 grams. So the percent of that is 3.24 grams that we just calculated over the 4.69 total grams times 100, or 69.1%. Ammonia can be used as part of the nitrophosphate process to produce the fertilizer blah, 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 which has the formula blah, 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 blah. So here's the equation, and I've already colored everything in. We know about the ammonia, told we got 1 ton of ammonia. We're asked about the mass of DAP, that's this stuff, in kilograms. So with the roadmap, what do we know about? We know about the ammonia, 1 million grams. And we're asked for the number of kilograms, or effectively grams on the roadmap, of the DAP here. Calculate the molar masses. Let's quickly make sure that this is correct for the DAP. Nitrogen 14, plus 4 is 18, times 2 is 36, plus 1 is 37, plus phosphorus, which is 31, gives us 68, plus 4 of the oxygens, 68 plus 64, is indeed 132 grams per mole. So, same stuff we've done all the way through. Take the million grams of ammonia and convert it to moles by dividing by 17 grams per mole, and we get 58,824 moles. That goes in this box here. Now in step 2, we need to use the coefficients, and finally we got some interesting coefficients, don't we? Okay, we've got the moles of substance B, which is the DAP, and the coefficient of the DAP is 3, so that goes on top, matching up the moles of DAP. And then on the bottom, we've got the moles of ammonia, 58,824 that we just calculated here, matching up with the coefficient of the ammonia, which is 8. Punch that through your calculator and you find that the moles of DAP is 22,059. Now, of course, converting that first of all to grams, we just take the number of moles, 22,059 moles, times the molar mass, 132 grams per mole. And that gives us, 2,911,764 grams, or realistically 2,912 kilograms. Should really have called it 2,910 for significant figures, because we got 3 significant figures in the tons of ammonia. Next one, cooking fuel contains butane, which reacts with oxygen according to. Now notice how naughty they are here, putting in a fractional coefficient, but it doesn't actually matter in terms of doing the calculation. So if 1 mole of butane reacts, calculate the number of molecules of carbon dioxide that will be formed. Well, this is kind of a fun one, isn't it? We're told about butane, and then we're asked about carbon dioxide. So we can still go through applying the processes that we know. First thing is, if we got moles of butane, we can go from moles of butane to moles of carbon dioxide using the equation that we've sorted out before. So moles of carbon dioxide over moles of butane. Coefficient of carbon dioxide is 4, coefficient of butane is 1. So thus we have 4 moles of carbon dioxide. Now we need to get the number of molecules for that. Well, 1 mole is 6.02 times 10 to the 23, so 4 is 4 times 6.02 times 10 to the 23, or 2.41 times 10 to the 24 molecules of carbon dioxide. Those who have gone through the movies for stoichiometry know that molecules is actually incorporated into a larger version of the roadmap, but I didn't feel it was appropriate to bring in the larger version of the roadmap for just effectively this one problem. Reaction sequence to produce 4-bromophenyl ethanoic acid. There we are. 4-bromophenyl ethanoic acid is shown below. Calculate the minimum mass of bromine. There's the minimum mass of bromine needed to convert 0.15 moles of 4-bromomethylbenzene. There's the 4-bromomethylbenzene to 4-bromo-1-bromomethylbenzene in the first stage. So there's the 4-bromo-1-bromomethylbenzene. Okay, so essentially we're looking at this first part of the reaction. So let's see, we are told things about the 4-bromomethylbenzene and we're asked about the bromine. So if we assign things here, we asked about the bromine, we're told about the 4-bromomethylbenzene, but we don't need all the stuff up here on the roadmap because we're already immediately told that we have 0.15 moles of the 4-bromomethylbenzene. So the first thing we got to do then is erroneously here called step 2, because we didn't need a step 1, and that is converting the moles of 4-bromomethylbenzene, that, to moles of bromine needed. And for that, we need the chemical equation. Okay, now let's make sure that we've got that right. We've got CH3Br plus Br2 goes to that nice little product there, but you've got to have something to do with the H that's been replaced by bromine, and so plus HBr. In other words, even though there's only 1 extra bromine atom needed here, we need a whole Br2 molecule to do the reaction. So that's moles of B, which is Br2, over the 0.15 moles that we start with, is a 1-to-1 reaction. And finally, mass of bromine, that's step 3, going from moles to grams. And so 0.15 times molar mass of Br2, 159.8 grams per mole, which is 23.97 grams. Relatively straightforward problem, of course, and indeed easier than the ones we've been doing because we didn't have to convert from grams to moles here. But I thought putting it at this stage just to emphasize the importance of getting the right equation there. Ammonia is produced when amide heated with aqueous sodium hydroxide. There we are. In experiment, 3.9 grams of the aliphatic amide T gave 0.06 moles of ammonia right there. Use this information to find the formula of the hydrocarbon group R present in the amide T. Isn't this a fun one? Well, anyway, it is a course starting off with a nice reaction. We've got moles of B equals coefficient of B, moles of A. Okay, so therefore the moles of the amide T divided by the ammonia, because that's what we're told and asked about, is 1 coefficient of T over 2 coefficient of ammonia. So therefore we've got 0.030 moles of T. Okay, now how does that help us? Well, because we also know that we had 3.9 grams of T. So in other words, 0.03 moles of T weighs 3.9 grams. So the molar mass, which is grams over mole, is 130 grams per mole. How does that help us? Well, because here's T. We know the whole molar mass is 130. We know we've got NH2, O, C, CO, and NH2. So what's left is the R. The formula of the R group can therefore be calculated. So R has a mass of 130 minus 88. Each of those CO, NH2 weighs 44. We got 2 of those. So R has a mass of 32. We're told that it is a aliphatic, so in other words there's no nasty little aromatic rings in there, and so 42 has to be equal to C3H6. If we had 2 carbons, 24, then there'd be 18 hydrogens. That's not realistic, and 4 carbons would weigh 48, which is of course too much. Slightly interesting little novel question. The important thing to realize is that this 3.9 grams of T is no use to you because you don't know what T is, at least at the start. So you have to use the ammonia to give you moles of T, at which point the 3.9 grams becomes useful to go with the moles of T to give you the molar mass and hence identify the R group. Finishing off this section with a question that we could use the roadmap for, but there are other ways to do certain stoichiometry questions, and it's worthwhile discussing those. So chloroethanoic acid, there we are, is produced from ethanoic acid, there we are, by producing chlorine gas into it under suitable conditions. In an experiment, 89 grams of ethanoic acid was reacted with chlorine. Calculate the increase in mass that occurs if chloroethanoic acid is the only organic product. So we could have done a roadmap. We could do 89 grams of ethanoic acid. That would be the grams of A, convert that to moles of ethanoic acid, convert that to moles of the chloroethanoic acid, which we would then convert to grams, and then we could calculate the increase in mass. Or, because we see, first of all, it's a nice one-to-one relationship, and what we're doing is we're essentially relating ethanoic acid to an extremely similar species, chloroethanoic acid, we can set it up as a ratio question. So we match up CH3COH to CCl3COOH, which has molar masses of 60 and 94.5 respectively. So the mass of the Cl, CH2, blah, 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 the mass of ethanoic acid, matching up the ratios with the molar masses, 94.5 over 60. Then, of course, we know the mass of ethanoic acid was 89. So we just multiply it through, and that gives us that the mass of Cl, CH2COH, the chloroethanoic acid, was 89 times 94.5 divided by 60, or 140.2. So the increase in mass is the 140.2 minus the 89, or 51.2 grams. Okay, just a quicker way to do it, and the only reason I'm doing it as the quicker way to do it is because I'm so good at the roadmap that I see, first of all, this is a one-to-one reaction, so therefore any moles of this will be the same as moles of that, so we can kind of remove those from consideration. And then because they are just so similar, only differing in replacing an H with a chlorine, that I can just go ahead and do the ratio. Nothing wrong, however, if you decide you wish to do this using the roadmap. Grams of ethanoic acid to moles of ethanoic acid to moles of chloroethanoic acid to grams of chloroethanoic acid, and you get this answer, and then the final step would be the same regardless of how you obtained that value.